Hello everyone, and welcome back. In this video, we're going to continue our conversation on the estimating of areas underneath curves using a variety of different approximations. So, thus far in the conversation, we've talked about left point, left endpoint, right endpoint, and midpoint approximations. And what we saw so far is that sometimes, depending on the concavity or the increasing decreasing nature of your function, this might result in either an over or an under approximation. And we introduced some notation to streamline this process. And what we want to begin with today is taking a look at another example like that, but instead of giving you the shape of the function, we're just going to give you the function itself, and then you have to draw it and figure out what the setup should look like. And so to that effect, that's where we'll begin. Here our function is g of x equals 3 plus 4x minus x squared. The minus x squared tells me that it's a parabola that, because of the negative out front of it, this is opening downward, so it kind of looks like a frowny face. It would probably help for us to know, for example, where's the vertex, and maybe where the x-intercepts are for this, so that we can have a rough idea of what this is supposed to look like. So let's write down some observations. So we're going to say, note, g of x is a parabola opening downward with zeros at, well, let's go ahead and solve for those. So the zeros are going to occur where the function is equal to 0. So that's the same as negative x squared plus 4x plus 3 is 0. And if you look at this for a couple of seconds, you might realize this is not going to factor super well. So as a result, we need to use the quadratic formula. This means x is going to be at negative b plus or minus the square root of b squared minus 4ac all over 2a. What's this going to be? This is 16 plus 12. That's going to be 28. So here we're looking at negative 4 plus or minus the square root of 28 over negative 2. 28, if I factor a 4 out of that, it comes out of the root as a 2. So this is the same as negative 4 plus or minus 2 root 7 over negative 2, which if I cancel with that negative 2 in the bottom, I'm getting 2 plus or minus root 7. It might also be helpful to know where the vertex, so we're going to say G's vertex is at, remember from pre-calc, x equals negative b over 2a. So that first part of the quadratic formula. So here we're getting negative 4 over negative 2, which is a 2. So maybe now we can start drawing a picture. So if I draw the picture over here, what I'm going to see is that I should have x-intercepts at 2 plus or minus root 7. 2 minus root 7 is going to be over here in the negative world. And we'll remind ourselves, we only care about what's happening from 1 to 4. So we don't really care about what's happening all the way over here. It might be worth noting that if I take 2 plus root 7, so we'll say, note 2 plus root 7, this is going to be bigger than 4, since root 7 is bigger than 2. So that's kind of worth noting, only because now we know the parabola is going to have, say, an x-intercept over here at 2 plus root 7, and then we might have a 2 here. So here's my vertex up here, maybe. Oops. And so as a result, and we also can notice, for example, my y-intercept is a 3, so that might be right here. And so the parabola I'm considering is going to look something like this. It's going to come up, it's going to hit that vertex, and then it's going to come down on that side like that, keep going. It'll look something like this. But we only care about what's happening from 1 to 4. So 1 might be over here, 4 might be over here, and 3 might be somewhere in the middle. So we only really care about what's happening in this region. So there's that left bound at 1 and that right bound at 4. So what we're trying to understand is the area inside this shaded region right here. So maybe I'll shade this in blue. So this is what we're interested in. Now, the question here asks us to approximate this area in a very specific way. The question here is saying that they want us to approximate this using midpoint sums with 6 rectangles of equal width. So to begin with, I'll come down here and I'll note that this entire region right here, this is of width 4 minus 1, which is 3. So each rectangle has a width of, well, it's going to be that right endpoint minus the left endpoint over the number of rectangles we want, which is 6. We just computed the top, that's a 3, so we have 3 over 6, which is a 1/2. So every rectangle that we consider has to have a width of 1/2. So we can come over here and we can sort of start to sketch out each of those rectangles. So here's one rectangle, 2, 3, 4, 5, 6. But what's more is we want midpoint approximations, right? So what that means is that for each of these rectangles, we want to consider the midpoint of it for that rectangle height. We should know what these values are going to be. But what we can see is that if one of these orange jumps is supposed to be a half, then each of the red jumps is going to be a quarter. So for example, this point right here should be 1 1/4. And similarly, this point right here is going to be 1 3/4. And you can continue in this fashion. You could turn these into improper fractions if you'd like. It doesn't really matter how you want to write it. Either way, we just need to know what these numbers are, because then what we're going to do is we're going to figure out what the sort of output for these are. So for example, this one looks all the way up here. 1 3/4 seems to come all the way up here. And then 2 1/4 seems to come all the way up here. 2 3/4 comes all the way up here. 3 1/4 comes up here. 3 3/4 comes up here. And those are my 6 midpoint approximations. So now I can turn around and I can say, okay, now I need to figure out what my corresponding rectangles are. So it looks like maybe it'll be this one. We'll redo that. There we go. So that's my first rectangle that I'm working with. Maybe I'll clean that up a little bit. And then we can continue in this fashion. So we can have this one come up and match the red dot there. We can have this one come up, match that red dot. And in some sense, this is just sort of the pattern that you start to adopt. So we're almost done here. And there you have it. These are 6 rectangles, each of which are being approximated using the midpoint of every single base. And you can see this is probably a pretty good approximation, right? Because like over here, we seem to be overcounting, but then undercounting. Or over-approximating and then under-approximating. So these might cancel each other out in some capacity, and we'll get a pretty good approximation at the end. So now the question remains of what is the actual sum of the areas of each of these rectangles? Well, let's start writing down what we want to try to say here. So what we're going to have here is we're going to have, so the area under g of x on 1 to 4, this is the area we're interested in, this is going to be approximately equal to the area we get after we use a midpoint approximation using 6 rectangles, so that's AM6. This is going to be written as, remember, we have that GCF of the common width, so that's 1/2, times the function values at every one of the midpoints, which, as I noted over here, would be 1 1/4, 1 3/4, 2 1/4, and so on. So this is going to be f of 1 1/4, which is otherwise known as 1 plus 1/4, otherwise known as 5/4, for example, plus f of 1 plus 3/4, plus f of 1 plus 5/4, plus f of 1 plus 7/4. And notice here, actually, I could be changing this up, right? Here I have 2 1/4. I don't have to write 1 plus 5/4, for example. I mean, I could have written this as 1 plus, 2 plus 1/4, for example. There's many, many different ways you could write this. And so maybe you could write 2 plus 3/4, for example, if that makes it work better in your head. Or you could just write them all as improper fractions right out the gate. But then we'll have 3 plus 1/4, and then 3 plus 3/4. And your next mission would be to actually compute each of these values, which admittedly is going to be a little bit taxing. It's a lot of fractions. So I'm going to encourage you to utilize a calculator for doing that, but I will not be computing this inside the video. So if you'd like to compute that and then come chat with me and show me your answer, I'm more than happy to take a look at it. But the whole point here is to reiterate how we might start with an arbitrary function, like here this quadratic, and then turn around and approximate the area under its curve using a midpoint sum with, in this case, 6 rectangles. So we had to do a little bit of pre-calc first to figure out how to graph our function so that we could then do the calculus on it. That's kind of the point of this example. So what exactly have we realized as we've done a bunch of these different examples? Well, one of the things that I tried to reiterate a bunch earlier in this overall conversation, and I'll reiterate here now in the video, is the following. The approximation gets better as you increase the number of rectangles. We saw that earlier in the conversation, right? We did a left point approximation with 1 rectangle, 2 rectangles, 3 rectangles, and we saw that indeed the more rectangles you allow, the closer your approximation, because you don't have so much error coming out of your sum. So this motivates the idea. If we cut up our region into, let's use a variable now, let's say n rectangles, each of the same width, and then you take the limit as n goes to infinity, that is, you let the number of rectangles go to infinity, then indeed we're going to achieve the true area. So sort of the picture that we always have in our head when we do this is that if we take an arbitrary function like this, f, bounded between, say, a and b, then what you want to do is squeeze in a large number of rectangles. So, for example, maybe over here on the left, we have this type of a rectangle. And we want them all to be of the same width. So maybe the next one looks like this. The next one looks like this. The next one looks like this, and so on and so forth. I'm not being particularly fancy with how I'm doing this. But the idea is that we squeeze in a whole lot of them. And maybe I'll put ... and then over here on the right, I'll have the rectangles coming in from the right. And this dot 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 is meant to indicate that we have an infinite number of these rectangles that we're considering. And we're also going to ask every single rectangle to have the same width. And remember the width formula that we had, right? So we have, in this case, we're working with n rectangles. So the width is going to be right endpoint minus left endpoint over the number of rectangles you're working with. And we're going to give this a name. We're going to call this delta x. This is, of course, familiar with our use of the derivative and how we designed that, and there's a reason for that. All will connect soon. But indeed, we'll say that the width is a small change in x, so that's going to be delta x. We're going to declare that in this context to be b minus a over n. That's that width. And indeed, if we do this and we take the number of rectangles, the number of orange rectangles, and we take the limit as n goes to infinity of the sum of those n rectangles, we're going to get the exact area under the curve. That's what we're going to get. So this becomes our plan of attack. No longer are we using just 1, 2, 4, 6 rectangles. We're going to use an infinite number of them. But we run into a little bit of a problem. We know how to take a limit. That's fine. However, when you want to ask this question, find the sum of the areas of n rectangles, this question is hard. It is difficult to find a formula that computes the sum of the areas of an arbitrary n rectangles. We can find sums of, say, 6 rectangles, like this. But as soon as this list becomes infinitely long, because you have infinitely many rectangles, this is a very difficult thing to compute. There's no way you're going to do this bit by bit. We need to have more powerful machinery that allows us to be able to condense our summing of large number of terms. And fortunately in math, we have something that handles that. And so we're going to introduce now something new. We're going to introduce something called sigma notation. And this might seem like a little bit of a departure, but it'll loop back soon. And so sigma notation is used explicitly when you want to sum finitely many numbers. That's what this green highlighted thing is. So we're going to suppose you want to take n many numbers, say a1 to an, and you want to add them all up. So you want to write down a1 plus a2 plus a3 all the way up to, say, an minus 1 plus an. So these are n many numbers all being added together using the subscripts 1 through n. We're going to condense this notation. We're going to use, since we're adding up a bunch of things, that's a sum. We're going to use the Greek letter S to stand for sum, so that's going to be a sigma. What I want you to notice is that over here on the left, the only thing changing is the subscript. So I'm going to introduce a dummy variable, say I, to represent that subscript. So I'm adding up a bunch of a sub i's as the i's, and I'll put the bottom down here, as the i's range from 1 all the way to n. So this I is referred to as an index. This a sub I is referred to as a summand, very similar to an integrand that we talked about earlier. And this is going to be the sigma notation that allows us to very succinctly write down a sum of items. And so the way this is read is that you start with I equals 1. If you put I equals 1 into this formula, you'll get a sub 1. That's over here. And then you add to that, now you uptick. Now you go from I equals 1 to I equals 2. Plug 2 into this, we'll get a 2. Then you add to that, well, now you uptick. Now you go from 3. Plug in 3, you get A3, and you continue doing that all the way until you hit N. So let's do some examples here so we can understand how this works. So here, for example, I'm adding up a bunch of even numbers. So I'm going to write this as sigma, some index, and now what I need is some formula that returns even numbers. Fortunately, what we know about even numbers is that even numbers can be written as something like 2i. They're all divisible by 2. But what does I need to start at? Well, I'm starting at 2, so I'm going to plug I equals 1 to begin with. And while you'll see when I is 1, we get 2. When I is 2, I get, oh, wait a minute. And now you look at this and say, well, wait a minute, I'm not actually looking at even numbers. So maybe I don't need the 2 here. Maybe I just need I. So I'm looking at I equals 1, I get 2. I equals 2, I'm sorry, I equals, okay, so I have to change the index as well. So here I'm going to change it to a 2. And so now I get I equals 2, I get a 2. I equals 3, I get a 3. I equals 4, I get a 4. 5, 5, 6, 6. So it looks like I'm ending at 6. Note that if you go on to take Calc 2, you'll spend a lot of time working with these things because there's a lot of other small changes one could make. Like, for example, equivalently, you could have written this as this formula I plus 1, and now you want your i's to start with 1, and it goes to 5. So I've sort of increased my formula by 1, but I've decreased my indices by 1. And it'll produce the same thing. If I plug in 1, I get 1 plus 1, which is 2. If I go up to 5, 5 plus 1 is 6. So these two things are the same. For example, here we have an arithmetic progression. So it's 3, 6, 9, 12, 15, 18. And so the observation we can make here is that I'm adding 3 every time. So this is going to be the sum of numbers, where in particular, since I'm adding 3 every time, I'm going to have this rule be something like 3i, and then we'll see what happens. So if I do I equals 1, so now I have I equals 1, plug that in, I get 3. Okay. I equals 2, I get 6. I equals 3, I get 9. So it looks like this works. These are all just multiples of 3. And I'm going to go all the way up to 6 as well. So this is a little trick you can start to learn. You look at the number of jumps you have, and that tells you what this should start looking like. Unsurprisingly, these are plus 1s, and that's why I used the 1i. What about this one down here? Here I have 2 fifths plus 3 sevenths plus 4 ninths. So the top have a pattern and the bottom have a pattern. So the top is a pattern we've already seen. That's just going to be I. The bottom have a different pattern. Here it looks like I'm adding 2. So that means I'm going to work with a 2i. But it's not that simple. Because if I plug in, for example, I equals 1. If I plug I equals 1 into 2i, I should be getting a 2. But instead I'm getting a 5. How do I get from 2 to 5? I have to add 3. So now I have, okay, I equals 2 is 4 plus 3, that's 7. I equals 3 gives me 6 plus 3, that's 9. So it looks like this is the correct pattern for the denominator. And it seems to be going up all the way to, but now there's a little bit of a problem. If I plug I equals 1 into the numerator, I'm getting a 1, not a 2. So I probably want to, instead of using I upstairs, I probably want to do I plus 1. And therefore, I want to go up to I equals 4. So this is how sigma notation is going to operate. This will take a little bit of getting used to, but it really is a magical tool that you absolutely need in order to effectively talk about these new calculus things that we're doing. Now, the goal is to write down using a sum of things as a sigma notation. So our eventual goal and what we're shooting for is when we get to stuff like this that we did earlier, this nice sum that we had here, ideally I don't want to have to compute that term by term by term. Ideally I want to have a quick way of just computing this overall sum without having to put that much effort into it. And that's kind of what we're sneaking up on. So these are ways to take sums of stuff and then condense them into sigma notation. Oh, somehow I lost my 4 here. We'll practice real quick the reverse. For example, here I have a bunch of sums and I want to write them out and determine their value. And this one's not so bad. So here I just want to plug in the index values. So L equals 5 is going to give me 15 plus 4 is 19. Plus, when I plug in L equals 6, I'm going to get 18 plus 4 is 22. Then I plug in L equals 7, I'm going to get 21 plus 4 is 25. And L equals 8, I'm going to get 28. And so that's going to be some final number. Similarly, this one down here, if I plug in 4, I'll get 4 over 4 plus 1, plus 5 over 5 plus 1, plus 6 over 6 plus 1, which in this case is 4/5 plus 5/6 plus 6/7, which again is going to be some sort of a number. And you can tell immediately that unpacking sigma notation is way easier than creating sigma notation, but we have to be able to do both. And similarly down here, we're going to get, what is this? If I plug in 1, I'm going to get a 3 minus 5. Plug in a 2, I'm going to get 12 minus 10. Plug in a 3, I'm going to get 27 minus 15. Plug in a 4, I'm going to get 16 times 3 is 48 minus 20, which again is a number. So again, the observation here is that unpacking a sigma notation is always easier than creating a sigma notation. So let's go back to our original point here. We said that we want to find a way to sum up these things quickly. So what I'm claiming is that if you have a sum of stuff and you turn it into sigma notation, that supposedly this should make our lives easier. How? How do I compute this sum, and how is that easier than just adding these numbers? Well, fortunately, we have some formulas that we can utilize. And these are 3 formulas. There are infinitely many out there, but these are 3 that you should commit to memory. In particular, the first 2. And what are they? They say that if I take, for example, the sum of a single number k, as k ranges from 1 to n, it turns out that this is just n times n plus 1 over 2. But remember, this is just 1 plus 2 plus 3 all the way up to n. So what this is saying is that if we have the formula 1 all the way up to a particular n, here's a very easy to compute way of doing that. This could be useful if, for example, this n value is like 55. You're not going to take out a calculator and go 1 plus 2 plus 3 plus 4 plus 5 all the way up to 55. Instead, you're going to use this formula, and you're going to go 55 times 56 divided by 2. Done. If you're curious why this formula works the way it works, come talk to me in my office. I'm happy to show you the proof for this. In a similar spirit, if I add up all the squares, so this is the same as 1 plus 4 plus 9 plus 16 all the way up to n squared. It turns out to be this formula. N times n plus 1 times 2n plus 1 times 6, or over 6. And if I add up all the cubes, this is the formula that we work. It's the same as the adding up all the numbers, the first one we looked at, but then we squared. So how is this useful? Well, look at these sums. Here I'm adding from 1 to 30 of this formula. I'm not going to go through and actually compute 30 terms of this. That would take a lot of time, and that would be a waste of the time that you spend. Instead, what I'm going to do is I'm going to rewrite this. I'm going to say, well, this is a sum of stuff, right? So because of the law of distribution, I can go ahead and rewrite this as, say, the sum from n equals 1 to 30 of 3n squared as an object minus the sum from n equals 1 to 30 of 2n. And in fact, we can do a little bit better because 3 and 2 in this instance are just constants. And we can factor out GCFs. So if I factor out a 3 here and a 2 here, there we go. This is really what I'm working with. And once you separate it out this way, we see that we have formulas for this. We have the n squared formula, that's the middle one, and then we have the n formula, which is the first one. Where here, 30 is the upper bound that we're working with. So this is going to be 3 times 30 times 31 times 61 all over 6 minus 2 times 30 times 31 over 2. And now, yeah, you'll still need a calculator to compute this overall sum, but it's way better than computing 30 terms of this first one. So it definitely streamlines the process and uses less computing power. What about this one over here? We have a nice cube. Well, kind of the big problem here is it looks like we're starting at a 3. That's kind of the rub that we have to pay attention to. Notice that the formulas up here all start with a 1. So I'm going to do a little bit of a trick here. I'm going to start by rewriting this as the full sum from 1 to 40. But then I'm going to subtract off the k equals 1 and k equals 2 term. So the k equals 2 term is 8 plus 8, and the k equals 1 term is 1 plus 4. So that's exactly what these are. This is k equals 2, and this is k equals 1. So I can always write the sum from, say, 3 to 40 as the sum from 1 to 40, but I just take off those first 2 terms. And I need that because this now I can use an actual formula with. So I'm going to rewrite this as the sum from k equals 1 to 40 of k cubed, plus 4 times the sum from k equals 1 to 40 of k, minus 21, which is those 2 extra bits. And I can now use my formulas. So this is going to become 40 times 41 over 2 quantity squared, plus 4 times 40 times 41 over 2, minus 21. So there's those formulas in action. And so these formulas allow us to be able to compute these sums really, really, really fast. So the overall plan of attack at this point is what we want to do is we want to come back to our Riemann, to our approximation, take this sum, write it in sigma notation, which is this notation, then use these formulas to write out our sums in terms of some closed formulas, and then we'll take a limit of those closed formulas. Let's put it all together. So our idea of area under the curve, pictorially, we had something like this. Here's my function f, bounded between an a and a b. So this is the area that we're interested in calculating. We agreed that we were going to take rectangles inside of equal width. So on and so forth. We also noted last time that the width of any individual rectangle is going to be called delta x, which we agreed was b minus a over n. And in particular, if we want to take a look at each one of, oh, sorry, this should be an A. So what that means now is that at any point that we're looking at here, like right here, this endpoint over here, for example, we're going to look at the interval. This is A to, what is this point right here? This should be thought of as A plus one copy of delta x. And then this point should be thought of as A plus two copies of delta x. So this should be maybe one copy of delta x. It should be two copies of delta x. And then this one should be thought of as A plus three copies of delta x, so on and so forth. So eventually, what you'll see is that the varying number is 1, 2, 3. So that's going to be the number of copies of delta x we want. So that's going to be represented by the value I. And so if we go ahead and do this process, the sum of each of these, the sum of all of these orange rectangles, we're going to give a new name for. That's going to be called a Riemann sum. So if we're given a function f on an interval a to b, then we're going to say that a Riemann sum is this sum. So what is this? This is the sum. We can write this out real quick. What is this? This is going to be the first rectangle. This first rectangle, the area of that is going to be height, which is going to be f of some value in between, say c1, times its width of that rectangle, which is delta x. So just to clarify here, somewhere in here is c1, so that this height right here is f of c1. So there's my f of c1 is that height of this first rectangle times the width, which we agreed is delta x. Then we're going to do the second one, which is f of a different input, c2, times that same uniform width, delta x. Plus all the way up to, eventually, all the way at the end, cn times delta x. So what we're going to do is we're going to take each of these delta x's and we're going to factor it out as a GCF. And then we're left with the sum of f of c1, f of c2, f of cn, which we're going to put all that into nice sigma notation. Where again, the delta x is exactly b minus a over n, and the ci is the number inside of whatever interval we're working with. So this is going to be the Riemann sums that allow us to help approximate the area under the curve. Notice that the cn here, or the ci, is any number inside this interval. It doesn't have to be the left endpoint or the right endpoint. It can be just any point in there, but traditionally we restrict ourselves to a particular type of point. So for example, here I have this cubic as drawn right here, and I want to find the area under the curve from 0 to 4. Specifically, using a Riemann sum, partitioning the interval into 8 equal length intervals, where the cn is the right endpoint. So let's draw a picture. For starters, actually, before we draw our picture, we're going to say note. Delta x is b minus a over n, that's the formula. B in this case is 4, a is 0, n is 8. So therefore we're getting 1/2. So if we come to this picture, we have 0 to 4, that's what we're working with, and I want intervals of 1/2. what I'm working with is 1/2, 1, which conveniently, I'm going to write 1 as 2 over 2, then 3 over 2, 4 over 2, 5 over 2, 6 over 2, 7 over 2, and 8 over 2. And I write it purposely like this so that I can see clearly that the only thing changing is the numerator 1, 2, 3, 4, 5, 6, 7, 8. That's going to be important. So now we want right endpoints for our rectangles. So what do we end up working with here? Well, we're going to end up with, say, this rectangle, this rectangle, this rectangle. Notice I'm using those right endpoints the entire way. There we have it. Right endpoints the entire way. And what you'll see here is that this is neither a strict over or strict under approximation. Some of these rectangles is an under approximation. Some of the rectangles are over approximations. This is because we're stuck using the right endpoint approximation, and our function is switching between concavities and increasing, decreasing, and so the shape of the function is informing the over or under approximation of our Riemann sum. And so now we're going to do the exact same process we did before. So we're going to say that the area under f of x on 0 to 4 is approximately, here we're doing a area with right endpoint sums using 8 rectangles. And here we know doing what we did before, this is the same as what would we write? We would say the first rectangle is 1/2 times f of 1/2 plus 1/2 times f of 2 over 2 plus 1/2 times f of 3 over 2. And we can do this over and over again. We're going to get f of 4 over 2. This is what we were doing before, right? 5 over 2. And hopefully, as you're going through this and you're writing all this out, you note to yourself, boy, this is cumbersome. If only there was a more efficient way of writing this. Well, there is. This is called sigma notation. The entire point here is, with everything I've written here, notice that the only thing changing is that numerator. So if I come in here and I drop an index variable, I seems to be ranging from 1 all the way up to 8. So instead, what I'm going to do is I'm going to write this as the sum, as the index goes from 1 to 8, of f of I over 2 times delta x, which is 1/2. This is my Riemann sum. So if I come up here and I compare and contrast the definition, look at this. This is the sum from I equals 1 to n of f of ci delta x. That's what I have right here. This is the sum to 8 of f of ci delta x. But the cool part is I can now use my formulas, so I don't have to compute 8 terms of this. That's going to annoy me. So instead, what I'm going to do is I'm going to compute this term by term. So, or rather, using sigma notation. So this is going to be what? Well, if I use my function definition, this is 1/2 times I over 2 cubed minus 2 times I over 2 squared plus I over 2 plus 3 all divided by 2. So this f of I over 2 is this bit right here. I just plugged I over 2 into my function. And now what do I want? Well, we're back in the situation like we were up here, for example. So I wanted to compute this sum of things with powers. So I kind of just pushed the sigma into the powers and left everything else alone. That's exactly what I have here. I have the powers, and I'm going to push this sigma into them and then leave all the other numbers alone. So we're going to end up getting here, we're going to get, well, the 1/2 stays on the outside. We're going to get 1/8. Well, here we're going to get 2 cubed, which is an 8, times the half. So that's at 1/16 times the sum from I equals 1 to 8 of I cubed minus, that's 2/4 is 1/2 times the sum from I equals 1 to 8 of I cubed plus 1/2 times the sum from I equals 1 to 8 of I. We'll put parentheses around this. Plus the sum from I equals 1 to 8 of just 3. So there I've pushed my sum into every single term that I'm considering. And now I have formulas for these, right? This is the cube. This should be the square, not the cube. And this is just the power 1. So I have formulas for these. So I'm going to get 1/2 times 1/16 times. Here I'm going to get 8 times 9/2 squared minus 1/2 times 8 times 9 times 17/2 plus 1/2 times 8 times 9/2 plus, and this is just 3 8 times, so that's going to be 3 times 8. And there you have it. With a calculator, you can compute what this number is going to turn into, but this is going to be far easier to compute than if I left you with these 8 terms in the beginning and you had to start plugging in 7 halves into this function and then figuring out what that number is. This is going to be obnoxious. This is maybe still obnoxious, but maybe less so. So this is what a Riemann sum is, and this is how we use Riemann sums to actually streamline the approximation of areas under the curve by using sigma notation. So this is where we'll pause in this video. In the next video, we're going to revisit this idea, but we're finally going to take a limit as the number of rectangles we use goes to infinity, and that'll actually allow us to compute the true area under the curve. So tune in next time, but for now we'll pause here, where all we've done is we've talked about Riemann sums, sigma notation, and how we can use this to streamline this process to get better approximations.